This is video 21.1. We will be looking at the magnetic force on a charged particle. The question: a 50 millicoulomb charge is traveling at 20 meters per second when all of a sudden a constant perpendicular magnetic field of 500 Gauss is turned on. We'd like to know, what is the force on the particle, the magnitude and the direction? And if the particle has a mass of 1 gram, what are the cyclotron radius and frequency? The meaning of these terms will be discussed on a future slide. Step 1 is to find the force on the particle. This is given by this equation called the Lorentz Force Law and states that the force on a charged particle is equal to the charge times the cross product of the velocity and the magnetic field. We know from earlier discussions about cross products that the magnitude of this vector is equal to QVB sine theta, where theta is the angle between V and B. The magnetic field was given in Gauss, but we want to convert it to the SI unit of Tesla. There are 10,000 Gauss in 1 Tesla, so we divide by 10,000 and we get 0.05 Tesla. 1 Tesla is equal to a volt times a second per meter squared. Plugging in what we know, a charge of 50 millicoulomb or 0.05 coulomb, 20 meters per second, 0.05 Tesla, and sine of 90 degrees because the magnetic field is perpendicular to the velocity of the particle. This is equal to 0.05 newtons. Now we'll use the right hand rule for the direction. Well, we know first of all from a cross product that the cross product of 2 vectors is perpendicular to both of those vectors. So if the particle is traveling in the x direction, the magnetic field is in the y direction, the force has to be in the z direction. We can find whether or not it's in the positive z or minus z by using the right hand rule. Looking at the bottom right hand corner of the screen, we imagine sticking our fingers from our right hand in the x direction, curling them in the y direction, and then our thumb is sticking out of the page, and out of the page is in the positive z direction. So that's the direction of the force on the charged particle. If the particle had a negative charge rather than a positive, it would be the other direction. Now the motion that the particle makes in a constant perpendicular magnetic field is a circle. That's because the force is always perpendicular to its velocity. So it moves a little bit and then the force adjusts so that it's always pointing towards the center. And we know that such an object, there's a centripetal acceleration and a force associated with that using Newton's second law of ma. So we want to find the cyclotron radius, the radius at which the particle makes an orbit within the magnetic field. Well, the force on the charged particle, which we just found, is also equal to mv squared over r by Newton's second law, because the centripetal acceleration is v squared over r and the mass m. So rearranging this, we have r equal to mv squared over f. Plugging in everything we know, this gives a radius of 8 meters. Now we'll find the cyclotron frequency. Recall that omega, which is the angular velocity, is v over r. We know v is 20, r is 8, so we have 20 over 8 radians per second. Or, if we would like it to be in hertz, we divide by 1 over 2 pi and this gives a frequency of approximately 0.4 hertz. And that concludes video 21.1. Check out PhysicsX on the app stores. This revolutionary physics app for smartphones and tablets contains over 100 videos and 500 multiple choice questions designed by education experts. It's been proven to improve scores for intro college physics, AP physics, MCAT physics, and more. Just look for the blue icon.